My name is Brandon White. I am an employee at Spring Discovery. I want to thank Recursion for sponsoring this event and the organizers for inviting me. Today I will be talking about Spring Discovery's published approach to finding therapies for severe COVID-19. The risk of death from COVID-19 drastically increases with age. Severe COVID-19 pathology is driven by both early and late immune dysfunction that we believe is closely related to aging. Given this, Spring's approach to finding COVID-19 therapies focuses on two questions. How is the old viral immune response different from the young response? And what compounds make the old response more like the young response? To answer these questions, we use the cell painting assay. Cell painting allows us to profile the key cellular organelles and understand the viral immune response at scale. Using cell painting, Spring images human primary PBMCs from hundreds of different donors. Her assay is able to image non-adherent cells through the optimization of key parameters such as plate adhesive, temperature control, and spin down protocol. He built a viral system using cell painting to understand how the old viral immune response is different from the young immune response. To do this, hundreds of young and old primary PBMCs were exposed to vesicular stomatitis virus. Monocytes were infected, which triggered a dose-dependent production of pro-inflammatory cytokines through a variety of pathways. Lymphocytes responded to the inflammatory environment in many different ways. Within this system, we observed many phenotypic differences between the young and the old viral immune response. To quantify these differences in the young and the old viral immune response, Spring built the multi-phenotype aging profile. From the cell painting images in a single well, we extracted several dozen features. The profile included targeted features which measure a specific biological process, and unbiased features which used the deep learning embeddings to capture all the information present in the entire image. Since the aging profile can be derived from a single well, He used it to screen thousands of compounds to find the one which make an old profile look like a young profile. One of the first targeted features we looked at was cell composition. He trained supervised and unsupervised algorithms to quantify changes in cell composition. We measured shifts in different immune cell types. A lot of these classes were shown to significantly correlate with traditional flow cytometry markers. We also quantified the composition of different types of cell death. Cell death pathways such as apoptosis, necrosis, and pyrotosis all induce specific methodologies which we built computational methods to quantify. As just one part of our aging profile, the compositional features I described showed significant differences between young and old. Old donors have a higher rate of infection with increase in infected monocytes, while the percentage of uninfected monocytes is unchanged between young and old donors. The opposite trend is true for the percentage of T cells. Upon viral exposure, the old donors experience a significant decrease in T cells. This decrease is only significant during viral exposure. We hypothesize that the differences in cell death that we observe could be driven by the differences in the young and old inflammatory responses. The major inflammatory cytokines, including IL-1 beta, IL-6, and TNF alpha, were all significantly elevated in the old donors. The old donors also had significant correlations between the increase in inflammatory cytokine levels and the decrease in the percentage of the T cells. The same correlation did not exist in the young donors. We had to account for batch effects and technical artifacts biasing our aging results. The key to overcoming these biases was specifically accounting for them in an experimental design which evenly distributed the young and the old donors across a plate. Our results were validated using both plate stratified cross validation and holding out of experimental batches. Besides targeted features, multi-phenotype aging profile also uses deep learning algorithms to model the young and the old viral immune response. The deep learning algorithms embed the images at the single cell level. Then the classifiers are trained on each individual cell type to predict a young response from an old response. The, the performance varied between 74 and 94 AUC depending on the cell type. It quantified many additional targeted features, including changes in physical cell-to-cell interaction and mitochondrial morphology. Her images serve as a biologically meaningful spatial point pattern that we used to measure how interaction between various cell types changes as we age. We also developed a method to measure the percentage of cells with reticular mitochondria or fragmented mitochondria. Both of these features were significantly different between young and old viral immune response. Those were just some of the differences we saw in the young and old viral response. There were many more features within our aging profile that showed significant differences between young and old. If all of these differences captured in our multi-phenotype aging profile, we then used it to find compounds which made the old profile more like the young profile. To do that, we screened thousands of FDA-approved compounds and ranked them by the two scores. The first score was an immune aging score, which measured the rejuvenating potential of a compound based off the aging profile. The second score was a COVID-19 cytokine score, which measured how a compound changes cytokines related to severe COVID-19. Using these two scores, we ranked thousands of compounds and chose the top ones for follow-up studies. One of the top ranking compounds in the screen was disulfiram. Disulfiram is a 60-year-old FDA approved generic with a robust safety profile that was originally approved to treat alcoholism. Within our screen, it made an old aging profile look like a young profile across multiple features. First off, disulfiram decreased cytokines IL-1 beta and IL-6. It also had a strong rejuvenating effect on the shape of the mitochondria by decreasing the percentage of T cells with particular mitochondria. Finally, it shifted the predictions of our aging classifier from being old to young. We hypothesized that these results could be driven by disulfiram's recently discovered ability to inhibit the terminal step of inflammasome activation by blocking gasdermin D. Blockage of gasdermin D not only prevents cytokine release, but it also prevents mitosis by blocking the release of neutrophil extracellular traps. Both inflammasome activation and mitosis are key drivers of severe COVID-19 pathology. Many studies have reported evidence of inflammasome activation by showing elevated levels of IL-1 beta and LDH in severe COVID-19 patients. Studies have also presented evidence of increased neutrophil lung infiltration and mitosis in severe COVID-19 patients. Together, both of these mechanisms are significant drivers of severe COVID-19 pathology. Given disulfiram's robust 60 safety profile and ability to block inflammasome activation and neutrophil mitosis, we have initiated a clinical trial to test disulfiram. The trial is a double-blinded, randomized, placebo-controlled study of 200 older patients with moderate COVID-19. The trial will start enrollment next week. Our multi-phenotype aging profile is able to understand many differences in the young and the old viral response. Using this profile, we surfaced the top candidates related to two key drivers of COVID-19. Inflammasome activation and netosis. Our top candidate, disulfiram, is able to block these drivers while also being safe, cheap, and globally available. Most companies would have overlooked disulfiram because it's a generic. Spring strongly believes that it has a huge opportunity for global impact. This is the team who worked on this, and our paper is up on bioRxiv. Thank you.